All right. This topic's a little odd because we hope that this doesn't happen. Most designs, everything I've talked about so far, except for the very simplest design, has assumed equal numbers of subjects per group, equal number of observations. Okay? So, except for really a vanilla one-way angle. You really want an equal number of observations per group. But you can't, maybe you don't. What do you do in that case? Well, the issue here is that the math, the underlying math, using sums of squares, the things I've taught you are called type 1 sums of squares. That should probably tell you there's other kinds. The problem is that they're affected by how many subjects there are per group. Think of all the little n's and stuff that are in there, right? So maybe we should try to do something about having those different numbers of observations. Well, what could we do? I've seen people estimate missing values. I don't know how useful that is. I think collect more data is the best approach here. Maybe use the mean or the median. This is the thing, when you estimate a missing value, so let's say you've got like 20 subjects, and 18, and you want to estimate the two more for the other 18, for 19 and 20. What number do you use? The average? Like the mean? The median? I don't know, those sound reasonable. But do you assume there's no main effects? Do you assume there's an interaction? I mean, these are tough questions. No matter what, you've lost degrees of freedom because you are now fixing more values. So it's not like you get degrees of freedom by adding in your own new numbers. I will say that I literally once saw this. I literally once saw a paper somehow get to me from a journal where they had just said, well, we didn't have enough observations, so we just doubled the numbers. And it's like, that's not a thing you can do. That's called making up data. You can't just make shit up and say, and then this happened. Amazing. Give me a Nobel Prize. It doesn't work like that. I was kind of surprised. But you can in certain circumstances, but you have to be very careful about it. Typically, you don't make up data. Typically, what you do is you go and get more subjects. It's the easiest thing to do. Okay. There's other ways to do this, though. So like I was saying, sort of tease this, most of our analyses use type 1 sums of squares. And that's what we teach you. We teach you type 1 sums of squares because, first of all, conceptually, they're easy to understand. They're deviations from means. That's something you've dealt with before, with variance and stuff. So, and they work perfectly if the n's are equal. So we teach you these because they're conceptually sensible and because, ideally, you would have equal n's. They're not as good when it's unequal. In fact, type 1 sums of squares are affected by, if there's an interaction, type 1 sums of squares care what order, this is going to sound really strange. Type 1 sums of squares care what order you do the math in, if there's an interaction. I know that sounds really weird, but it works that way. Sorry, that's type 2s. We'll talk about this in a sec. Type 1s, yeah, I made a mistake there. Type 1s, the big problem is that if there's an interaction. And if there is an interaction, then the order you do the calculations in matters, which is kind of weird. So type 2s, this is good when we have a missing value because it can help us estimate them. Okay? Oops. They're also bad. See, the nice thing with type 2s is they can go, oh, there's some missing values. We can figure that out, no problem. But the more variance there is in your design, the worse type 2 sums of squares get to actually estimating what really happened. The way you do this is you do this by doing what are called Monte Carlo experiments. You make up a big data set and then you do the analyses and see how accurate it actually is because you have the population scores. So type 2s aren't great either. Type 2s have a very specific purpose. They're really useful in multiple regression, and we'll talk about them literally next week. Now, type 3 sums of squares, I don't know how to calculate, but I know my computer does. Well, I know how it's done. It's using matrix algebra, which I can't do. I'm not very good at it. Okay. You probably don't know if there's an interaction, because if you knew, you wouldn't do the experiment, right? So type 3s are safe. So, I've been teaching you type 1s, but all the outputs you get from your printouts from SPSS or PSPP are type 3s. And type 3s equal type 2s equal type 1s if you have equal number of subjects. So the reason why it doesn't matter that I haven't taught you type 3 sums of squares is I'm just telling you, just have equal number of subjects and you'll be fine. Then I don't have to teach you all this crap. Which is, again, beyond this. If this isn't a statistics class for the sake of statistics, we use this as a, what do you call it, a tool, right? So we've learned type 1 analyses. Our software all uses type 3s. So the nice thing is you're safe if you have unequal ends and you're using software to do your analysis. And if your ends are equal to type 1s, equal to type 2s, equal to type 3s. Okay. So it doesn't matter if your ends are equal. It's as soon as the ends are unequal where things get weird. And I can actually show you an example of this. This is just some cooked up data these are just some data I made up and then analyzed. I don't even have the data on me, but yeah, you can see here. Okay, it's hard to see. I think on that screen you can hardly read it. So look at the screen here. This is a type 1 analysis, a type 2 analysis, and a type 3 analysis. So the columns are kind of weird, but look what the A is. So 3.125 is the sum of squares, so the mean square is 3.125, and then the type 2 mean square is 2.7, and the type 3 mean square is 3.199. They're all different because I've got I made an unbalanced design up, and I just made up some numbers and made them unbalanced. So we have one level of A, 4 levels of B, and a total of 33 observations. Notice how some things are the same. The error mean square is the same all the way through. But you see what's changing. And the interaction one isn't changing. But what's changing is the effect of A. So you don't want that. So just have an equal number of subjects and everything's fine. If you don't have an equal number of subjects, it's not the end of the world because your software will use type 3s and they'll be accurate. But I wanted to let you know that this is a proper concern. It's a real thing to care about. Now there's another one. This is the last one I've heard of. Maybe there's a type 5 I haven't heard of. Type 4 sums of squares are kind of hilarious. They work with empty cells. So let's say you've got a 2x2 design, but you got one whole cell missing. Type 4s come up with a solution to the problem, what should be there. It's not a unique solution. In other words, they come up with a solution that works, but there's other ones. In fact, there's literally an infinite number of other ones that work. If you have an empty cell, you don't know what number goes there. What type 4 sums of squares do is they calculate, they have an algorithm that calculates how it works. That's all you need to care about. Type 4 sums of squares are really interesting to, who? Statisticians. For us, screw them. We wouldn't do this. What would you do in this situation? Let's not even worry about numbers for subjects, like individuals. What number goes here? Let's say these are group means. What number goes there? I don't know. Well, 4 looks nice because it'd be an interaction. Could be a 2. Could be that just this one's bigger than all the other 3. It could be 1,000,000. It could be minus 406.2. I don't know what it is. Those are all perfectly reasonable answers, assuming the scale goes from minus 406 up to 1,000,000. Those are all perfectly reasonable answers. We have no idea what goes there. Right? We have no idea what goes there. I think all of us immediately go, well, 4, because it just looks nice. But no, it doesn't have to be 4. There doesn't have to be a pure interaction and domain effect. It could be anything. How would you, let's say you've done this experiment, and let's say that the A2, B2 actually makes no sense. You either couldn't combine the two, or, I don't know, let's see, what else? Or it just makes no sense to combine. You know, you've run out of time. You're doing your honors thesis, it's next year, you're doing your honors thesis, it's the day before the poster presentation. You've got all your data collected except for that one cell. And you come to me and I say, what the hell's wrong with you? Why didn't you collect data there? Well, I haven't done it yet, Dave. Okay, fine. You gotta put something on your poster. How are we gonna analyze it? What would you do? We care if the groups are different, right? We still would care. I'd just do a 3-way, like a simple ANOVA with 3 groups. That's what I'd do in this case. At least I'd have something. I can say the groups were different. I can't talk about interactions, because you can't with a simple ANOVA, but at least I can say something. So there's ways around it. The worst thing to do is make up data. No, sorry. The very worst thing to do is have empty cells. The next worst thing to do is make up data. Well, the very worst thing to do is make up data and don't tell anybody you made up data. That's just called academic dishonesty, but that's an entirely different discussion. Right? So what I would do here is I would probably, if I couldn't get these data, and let's say we can't, I would just do a 1-way ANOVA using these 3 means. And then when somebody asks me at the thesis conference, why didn't you look at cell A2B2? Didn't have enough time to do that. And that's a good answer. The important thing about empty cells is don't have them. Just don't do it and you'll be fine. So Latin squares, as we talked about today, are great under very specific circumstances. Empty cells are never good, but you can deal with them. But the best way to deal with them is collect more data so you don't have empty cells. Unbalanced isn't bad. Unbalanced, our type 3 sums of squares deal with it fine. Balanced is nicer, but unbalanced is fine. But empty cells, you just don't have them. And if you do, you can't look for interactions and stuff like that. There are other ways to do this. I'm talking about using the stuff we've talked about here. All right. So any questions on that? It's not bad, right? Hey, you know what we just finished? We just finished talking about analysis variance. Now we can talk about regression next week. Yay, multiple regression. Multiple regression's cool. If you think this stuff's weird, what I like about multiple regression is it's kind of a lot more judgment calls, so I think you'll like it.